In this video, we're going to explain how to properly change coordinates when computing these multivariable integrals. So the first thing, we need to generalize this formula that we have relating these two things. So in general, if R is a region in Rn and f is a function from Rn to R, basically I just generalize exactly the way I would expect. So the integral of f dx1 wedge all the way out to dxn is just equal to sort of the n-fold integral over the region R of f times dx1, or sorry, not really times. I mean, this doesn't really make any sense, this notation here, but just sort of the normal integral in x from x1 to xn over R. So this generalizes the formula that we had before. So what we're going to do with the rest of this video is prove a change of coordinates formula. So if I have some map phi from Rn x1 through xn coordinates to Rn phi1 through phi n coordinates. So what this means is that phi takes x1 through xn to phi1 of x1 through xn, etc. So the phi's are the coordinate functions. And this is invertible and differentiable, and its inverse is differentiable. Then we get the formula, the integral of f over the region R dx1 wedge dxn is equal to the integral over the region phi of R of f composed with phi inverse times phi inverse pullback of dx1 wedge all the way out to dxn. So this is what your book writes. One thing I want you to note that I think really makes this formula super easy to remember is that the pullback on a zero form is just composition, right? So I can actually rewrite this as phi inverse pullback of f times dx1 wedge all the way out to dxn. And what I'm going to get, I mean, even here, but what I'm going to get is another n form on Rn, right? But n forms on Rn are all of the form of function times a volume form. And so I can really use this framework that I've set up to integrate them. So basically, this is what we're going to prove. Okay, so we're going to prove it by basically going through our, going through our Riemann sum procedure that we did to prove, how to integrate just a regular function on R2. We're going to go through that and explain how this formula continues to work in that setting. So first of all, we're going to have to choose a lattice of points. This gets a little bit more complicated, but we're going to choose a lattice of points. So I'm going to choose like xi1, where I1 goes from 1 to M1 all the way out to xin, where in goes from 1 to mn. So this is sort of the higher dimensional version of these x's and y's here. Then I can consider, all of the tuples xi1 through xin in R, my region R, and this produces some set of points, phi of xi1 all the way out through phi of xin, which I'm going to just call, so these are elements of phi of R. I'm going to rename these to just be phi of I1 all the way out through phi of in, just because, for conciseness. And this might not be a nice neat lattice, but it will still be some set of points that kind of forms a mesh throughout my region, because phi is invertible, so it can't sort of squish anything too terribly. Okay, so then in analogy to the second step, I'm going to define the vector v1 I1 through in to be the vector where I just take the difference of the first two coordinates. So x I1 plus 1 minus x I1, and then the rest are zeros at the point x I1 all the way to xin, and keep going all the way down to vn at I1 through in, is equal to 0, 0, x in plus 1 minus x in at the same point. Okay, so, and I can consider, so right, these are all elements of the tangent space at xi1 through xin of Rn. Okay, so then when I want to rewrite, so now I'm going to rewrite my integrand. So at this point before, I was sort of explaining like what this area was. And I'm going to show you that that area is given in sort of, I can compute it in a different way using phi. So, so what I want to show first is I want to understand what the dx1 wedge all the way out to dx n v1 I1 through in all the way out to vn I1 through in is equal to. So it doesn't hurt to just throw in a, so remember my integrand is f dx1 wedge all the way out to dxn. And the sort of, maybe integrand is like the wrong thing to say here. I want to rewrite the terms in my sum. So these should be something like f x1 xi1 through xin times dx1 wedge all the way out to dxn at applied to v1 blah 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 all the way out to vn blah blah blah, where blah 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 is this thing I1 through in. Okay, so first let's focus on this second part. So it doesn't hurt to just pull back by sort of multiply every vj at I1 through in by the identity matrix. So I'm going to take d phi inverse and compose it with d phi. That's the identity, and apply it to v1 through at v1 I1 through in. And you know what? At this point, I'm just going to call this v1 and vn because there are too many subscripts and it's too confusing. Okay, so I'm just applying d phi inverse composed with d phi at each of these vectors. They're all the identity, so it doesn't matter. Now, this is exactly how I write phi inverse pullback of dx1 wedge all the way out to dxn of d phi v1 all the way out to d phi vn. So that's just a different way to write this term here. Okay, so now I want to rewrite the first term. So f of x1 through xi1 through xin is the same thing as f composed with phi inverse composed with phi of xi1 through xin. Basically, we're just doing what we did for the volume form, just at the level of points. So this is just phi I1 through phi in. This is just, using my notation. So I can also write this as phi inverse pullback of f, but I'll just leave it. So what I end up getting is that the whole sum, right, f of x1 at xi1 through xin times dx1 wedge all the way out to dxn applied to v1 through vn is just equal to f composed with phi inverse at phi I1 all the way out to phi in, that n does not look like an n, times dx times phi inverse pullback dx1 wedge all the way out to dxn applied to d phi v1 all the way out to d phi vn. So that's exactly what I showed. Okay, so the fourth step was basically add it all up and take the limit. So, so as we so basically we just end up getting, like, on the left hand side, or sort of when we take the add this all up and take the limit, add overall overall xi1 through xi(n)s, and we take the limit as sort of m1 through mn go to infinity. Remember, this is the number, so m1 was like the number of xi1s I had. Mn is the number of xin(s) I had. We get, on the one hand, the integral over r of f dx1 wedge all the way out to dxn. And on the right-hand side, okay, so what are we really plugging in? Well, we're really plugging in, the, like, exactly what we would have computed using the lattice of points phi I1 through phi IN. So we're getting the exact same integral, and we've shown it's the exact same integral, but we're using a different form, a different function in a different form to compute it. So we get the integral over phi of r, because we're plugging in points in phi of r, of phi inverse pullback of f dx1 wedge all the way out to dxn. And remember, because we're computing, we want to be looking at the differences between points. So these should be d phi v1 is sort of the difference in between the points sort of the points x xi, well, sort of xi1 plus 1 and xi 1, and then setting all the other coordinates to be 0. But remember, this is a vector, so this is again at the point phi I1 through phi IN. Okay, so we've gotten what we wanted. Okay, so what we'll do next is compute some examples.